In this section, we will focus on properties of gases. We will study all the molecules who are gases at room temperature. Every time we breathe, we inhale air, which is a mixture of gases. Natural gas is used as a fuel for combustion reactions that we use to cook our food. Gases are also used in medicines as anesthetic because of their unique ability to pass through tissues and through the blood-brain barrier. So gases serve important part of our everyday life. So before we examine the macroscopic properties of gases in more detail, let us review the behavior of molecules or atoms at molecular level. So this level is known as kinetic molecular level. So kinetic molecular view describes the behavior of gases at molecular level. So if we have any gas inside a container, for example, this is a container and these spherical particles represent molecules or atoms of gas. So these atoms and molecules uh, are in constant motion in random directions. And these particles move at relatively high speed. So greater the speed, the greater will be their kinetic energy and greater will be the temperature of the gas. So in other words, the speed of the molecules or atoms depend on the temperature. Higher temperature means the molecules of those gases are moving at higher speed, and higher speed means that they have greater kinetic energy. The atoms or molecules of gases, they move in straight lines but in random direction. And when they are moving, they may collide with other particles or with the walls of the container. For example, so this molecule can also collide with the walls of the container. And that's why they fill the entire volume of the container because they are moving in random directions. So they occupy the entire space available within the container. Although in this picture it looks like the container has large gas particles, but the reality is that the size of these particles is extremely small as compared to the overall size of the container. So therefore, although in this diagram or picture they look like molecules are quite close to each other, but in reality gases, atoms and molecules are far apart from one another. So therefore they have negligible intermolecular forces of attraction. So because of the great distance between two molecules, the forces of attraction does not really exist in gases. Gases have unique properties which is different from solids and liquid states because gases are compressible, which means that the volume of gas can be reduced. For example, if we have a container full of gas molecules, let's imagine these are mixer. Uh, this container, if it has a movable piston, can be compressed, and after compression we can compress the gas particles close together. So this is a unique property of gases. So because of this, pressure becomes important property or parameter in gases. Now what is pressure? According to kinetic molecular view, pressure of a gas is the result of the force of atoms or molecules colliding with the walls of the container. As we defined earlier that the molecules are randomly moving, and when they are moving in such a way that they collide with the walls of the container also. For example, imagine if this is the wall of the container and the red spheres are the particles, so they are hitting the wall, and when they hit, then they bounce back and then they start moving in some other direction, and some other molecule will come and hit the wall, and so on. So at any given time, a large number of molecules, billions and billions of gas particles are colliding with the wall, and each of these collision will exert some force on the wall, some force on the small section of the wall. So pressure is that force divided by area. Each molecule collision exert a extremely small amount of force, but if we combine the effect of all those billions and billions of molecules, this force becomes quite considerable, and therefore gases may have considerable amount of pressure within a container. Let's apply the concept of kinetic molecular view of gases and figure out which of these statement is incorrect. First statement is gas particles are in constant motion. This is correct. Kinetic molecular theory explains that gas particles are always in constant motion. Second is greater speed occur at higher temperature. This is also correct because the kinetic energy is dependent on the temperature of the gas. Third, gas particles collide with each other and form attractions. Although the first section is correct, gas particles do collide with each other. However, they do not have any attractions. That's the main point. So this is incorrect. Because of this, this statement is not totally correct. Gas particles fill the entire container. This is correct because they are randomly moving in all directions. Therefore, they fill the entire container. And gas particles move in straight lines in random direction. That is also correct. So only incorrect statement is this one. Gas particles do not have any significant amount of attractions with each other. So as we learn, the pressure of a gas is equal to the force exerted by the particles of the gas when they are hitting the walls of the container per unit area. So pressure is equals to force per unit area. Pressure can be measured in many units. The most common unit is atmosphere or ATM. Other common units of pressure are millimeters of mercury, is denoted by mmHg, or TOR is pronounced TOR, and PSI stands for pounds per square inch, and pascals, and the abbreviation for Pascal is PA. So all of these units are pressure units, and 1 atmospheric pressure is equal to 760 millimeters of mercury, or 760 torr, or 1 atmosphere is equals to 14.70 psi, or 1 atmosphere is equals to 101,325 pascals. So we can use all of these relationships as a conversion factor when we want to convert 1 unit of atmosphere to another unit of atmosphere. So we said that the most common unit of pressure is ATM. ATM stands for atmosphere. Now, what is the meaning of atmospheric pressure or ATM? So on the planet Earth, we have atmosphere around the planet, and this atmosphere is mainly composed of nitrogen gas. 78% of the air around the planet Earth is nitrogen, 21% is oxygen, and then remaining 1% is a combination of all the gases such as argon, carbon dioxide, water vapor, and some minor amounts of sulfur dioxide and nitric oxide, and all other gases. So around the planet Earth, if this is the planet, we have a blanket of all the gases. So that blanket of all the mixture of gases is our atmosphere. Now, because of the gravity of the planet Earth, the molecules of the air or different gases, they compress the surface, or they hit the surface all the time. Okay, so the force of air molecules pressing on the earth due to gravity per unit area is the pressure of atmosphere. So at sea level, atmospheric pressure is defined as 1 atm or 1 atmosphere. So that's the meaning of atmospheric pressure. As we go up on the mountains, as the elevation rises, the pressure decreases. So therefore, the standard atmospheric pressure is measured at sea level, and it's is equal to 1 atm. Now, how do we measure pressure of any atmosphere? We use a device called barometer. Now, barometer uh, has a tube filled of a heavy liquid such as mercury. In fact, it is filled up with mercury, and the tube is sealed on one end, and its vacuum is created in that end. There's no pressure inside the tube, and the barometer is open from the outside. So the atmospheric pressure will push the liquid down, and there is nowhere else for this liquid to go. So because of the atmospheric pressure, the liquid will start rising. The liquid in this case is mercury, and at sea level the pressure is enough to push this liquid all the way up to 760 millimeters. And because uh, it is filled up with the mercury, so we call this 760 millimeters of mercury. Hg is the symbol of mercury. So this is the pressure of one atmosphere. If the barometer is exposed to lower pressure, such as up on the mountain, then of course the mercury will not rise all the way up to 760 millimeter. It may rise maybe slightly less, maybe 750, and so on. So depending on how much is the pressure outside, the rise in the tube, the rise of mercury in the tube will tell us what is the pressure of that area. Okay, so at sea level, the height of mercury in the tube is 760 mm of mercury. This is same as torr. So 1 Hg millimeter mercury is equals to 1 torr. So that's the definition of torr, unit of. So therefore 760 mm mercury or 760 torr. As we defined earlier, that at sea level the pressure of our atmosphere is 1 atm. As we go on higher altitude, the atmospheric pressure starts decreasing because there is less air. So as you can see that if you go to Denver, which is mile high city, the average elevation of mountains there is about 3,000 meters. The pressure drops to about 0.83 atmospheres. On the top of highest mountain, Mount Everest, the atmospheric pressure is only 0.33. So in other words, there's only 1/3 of air present as compared to the sea level, because sea level is 1 atmosphere, top of the Mount Everest is 0.33. So as we go up, the density of air decreases, the atmospheric pressure decreases, which means there's less air available. Less air available means less oxygen available. That's why at higher elevation we experience loss of breath, because there is less oxygen available per breath. So we hyperventilate, and many mountain climbers, they do carry special oxygen tanks to breathe, because at high elevation loss of oxygen can be fatal. When a jet is flying at cruising altitudes, uh, which is typically at around 10,000 meters, which equates to about 30,000 feet, the cabin of the plane is pressurized to 0.75 atmosphere. Why? Because outside air pressure is only 0.27 atmosphere, which is extremely low for any human to breathe. Our ears notice the change in pressure as the plane ascends to cruising altitudes because the air behind the eardrum is at higher pressure uh, than the external pressure of the cabin. So the eardrums bulges outward and eventually the pressure inside the air is equalized to the lower cabin pressure, and that's when the ears pop. Pressure is one of the unique property of all the gases. But to understand the behavior of gases, we need to consider not only pressure but all four of the interrelated variables that describe the macroscopic properties of gases. So these four variables are pressure, of course, and then volume of a gas, temperature, and number of moles. Combination of these four variables describe the behavior of any gas. The relationship between these four variables have been studied since 17th century, and simple gas laws have been developed which describe the behavior of a gas based on these variables. The gas laws are mathematical relationship between two variables that reliably predict how a change in one variable will affect the other variable when the remaining variables are constant. In the science, law is an accepted hypothesis that has demonstrated over time its predictive value. So in next few sections, we will take a look at three different laws which relate two of the variables out of these four variables. There are three simple gas laws. Now, simple gas laws are those laws which relate two variables out of four. Uh, the relationship between the pressure and volume is defined by Boyle's law. Relationship between volume and temperature is defined by Charles' law. And the pressure and volume relationship is given by Gay-Lussac's law. According to Boyle's law, pressure and volume are inversely proportional to each other when number of moles and temperature are constant. According to Charles' law, volume and temperature are directly proportional when number of moles and pressure are constant. And according to Gay-Lussac's law, pressure and temperature are directly proportional when number of moles and volume are constant. Now, in all these laws, we saw the term inversely proportional and directly proportional. So now what's the meaning of inversely proportional and directly proportional? Inversely proportional means if we increase one variable, if the other variable goes down, so this relationship is known as inversely proportional relationship. And directly proportional is that if one variable goes up, the other also goes up. That is known as directly proportional to each other. For example, the pressure and volume are directly proportional. So that means, according to Gay-Lussac, if pressure of a gas goes up, then the volume will also go up. So that's the meaning of directly proportional. So now let's take a look at Boyle's law. So Boyle's law states that pressure and volume are inversely proportional. So it means that if the pressure of a gas goes up, its volume will go down. So that's the meaning of inversely proportional. Similarly, according to Charles' law, volume and temperature are directly proportional. It means if the volume of a gas goes up, then the temperature will also go up. In fact, it's the opposite. If the temperature goes up, volume will also goes up. So that's the meaning of inversely proportional and directly proportional relationships. Let's learn about these laws in detail now. So first law is Boyle's law. Boyle's law gives relationship between pressure of a gas and volume of a gas. The other two parameters, that is the number of moles and temperature, remain constant. So this is important that during Boyle's law, the number of moles and temperature of gas do not change. So according to Boyle's law, pressure and volume are inversely related to each other. What does that mean? Let's consider a container. For example, in this case, this container contains some amount of gas. So this gas has some pressure on it because it is connected to a movable piston, and piston has some mass, and that mass is putting some pressure on it. So let's call this pressure P1, or PI means initial pressure. And this gas under PI pressure is occupying this much space inside the container. So let's call this volume VI. VI means initial volume. Now, if we increase the pressure by putting more weight, so if we put more weight, of course, the pressure has increased, right? So as we can see, as we increase the pressure, look at what happened to the volume. So the new volume now is V, let's call this V final. Let's call the new pressure P final. We can obviously tell that P final is more because there is more mass. So P final is more. More means it's high pressure. But what happened to volume? Volume is less. So in other words, as pressure went up, the volume of gas went down. So this kind of relationship is known as inverse proportionality relationship. So if we plot a graph between pressure and volume, so pressure on this axis and volume on this axis, we will see that as pressure is decreased, the volume of gas will increase. So the graph will be this way. So low pressure, so the volume will be high. On the other hand, if we plot a graph between pressure and 1 over V, then the pressure versus graph will be a straight line. And Boyle also discovered that the product of pressure times volume at any state will be equal to pressure times volume of any other state. For example, if we multiply the starting pressure with the starting volume, it will be same as final pressure and final volume. Why? Because if one component goes up, the other one goes down, so the product of those two components remains the same. So this relationship or this equation is used to solve problems related to Boyle's law. So Boyle's law can be summarized as PIVI equals PFVF. Sometimes we also write it P1V1 equals P2V2, where 1 means first or initial state and 2 means the final state. We'll take a look at a problem and we'll see how we can apply Boyle's law to find unknown pressure or unknown volume of a gas. A sample of a gas in 1 liter container at 1 atmosphere of pressure is placed into larger container. What happens to the pressure? Okay, so let's draw a picture what happened. So we have a gas inside a container. So volume of this container is 1 liter and pressure inside the gas is also 1 atmosphere. Now this gas is transferred to a bigger, larger container. Okay, so as we can see, the larger container means V is greater than 1 liter because it's more, right? So volume has increased, right? And we know from Boyle's law that pressure and volume are inversely proportional to each other. If one value goes up, the other one goes down. So let's see what choice makes more sense. So what happens to the pressure? the pressure decreases, and that is correct because volume went up. So that means according to Boyle's law, pressure must go down. The pressure increases, that is incorrect. The pressure stays same, that is also incorrect. Not enough information is given, that is also incorrect. So the correct answer is pressure will decrease. Which relationship is inverse? Temperature to pressure, volume to temperature, volume to moles, and pressure to volume. And we know that only pressure and volume relationship is inverse. That's Boyle's law. So correct answer is pressure to volume. The pressure gauge on patient's full 10.7 liter oxygen cylinder reads 8.5 atmosphere. Okay, so we have a uh, oxygen tank or a cylinder, and it has a pressure reading gauge, and pressure inside, so pressure inside the cylinder is 8.5 atm, and the volume of this cylinder is 10.7 liters. All right, so these two numbers are given at constant temperature. That means temperature does not change, so we don't have to worry about it. How many liters of oxygen can the patient's tank deliver at a pressure of 0.92? Okay, so now we are having a situation in which our starting pressure is given and starting volume is also given, and we want to figure out that if we decrease the pressure is decreased to 0.92 atm. So this is our final pressure. So this one is initial pressure and this volume is initial volume. So if the final pressure is decreased to 0.92, how much will be the final volume? That's what we want to find. How many liters of oxygen can the patient's tank deliver at a new pressure of 0.92? Okay, so let's write this up cleanly. So according to this statement, so what values are given? So given values are, our starting value of pressure is given, Pi is 8.5 atm, and Vi initial volume is also given, 10.7 liters, and P final is also given, 0.92 atm. And what do we want to find? We want to find the final volume. This is unknown. According to Boyle's law, the Boyle's law equation is PIVI equals PFVF. So in this equation, we already know the value of Pi, we already know the value of Vi, and P final is also given. So only one is unknown, Vf, so we can uh, plug in the values and we can figure it out. Before we do that, let's reshuffle the equation and bring Vf on one side and everything else on the other side. So we need to divide both sides by Pf. When we do that, the equation changes to PIVI divided by Pf. So let's plug in the values. Pi is 8.5 atm multiplied by Vi is 10.7 liters divided by Pf value is 0.92 atm. Atm cancels with atm, only unit left is liters. Let's solve this equation. So when we multiply 8.5 with 10.7, we get 90.95 liters divided by 0.92. So let's divide that number with 0.92, and the answer comes out to be 98.6 liters. So that is the answer. The relationship between volume and temperature for a fixed amount of gas at constant pressure is known as Charles' law. Charles' law states that volume and temperature are directly proportional to each other, which means that if temperature of a gas goes up, volume will also goes up. For example, in this picture, you can see that there are two containers and they both contain same amount of gas and they both have same pressure because the mass which is holding the piston is same. The first gas is at temperature 200 Kelvin and the other gas is at temperature 400 Kelvin. And because as the temperature increases, the kinetic energy of these particles will increase and these particles will move faster and hence they will expand. We know increase in temperature causes expansion. So therefore, Charles' law states that temperature increase will result in increase in volume. A graph between volume of a gas and temperature will be a straight line crossing the x-axis at 0 Kelvin. In order for Charles' law to work, the temperature must be expressed in the unit kelvins. So at high temperature, we have some volume of a gas at some temperature. As the temperature goes down, the volume also goes down, so it will be a straight line. And at some point, the volume line crosses the x-axis. So this temperature where the volume line crosses the x-axis, this temperature is 0 Kelvin. It looks like okay, but it's a 0 Kelvin. So 0 Kelvin is the temperature at which the volume of any gas becomes 0. That's so. So this is the absolute zero temperature of any gas. The value of absolute temperature or absolute zero is negative 273 degrees Celsius, or it is also equals to 0 Kelvin. So therefore we can say that at 0 Kelvin a gas has no volume and particle of that gas will have no kinetic energy. When doing calculations using Charles' law, temperature must be given in kelvins. So temperature must be in Kelvin scale. If it's not in Kelvin scale, then it must be converted into Kelvin. And remember, temperature Kelvin is equals to temperature degrees Celsius plus 273. So this is the conversion factor between Kelvin temperature scale and Celsius temperature scale. The mathematical relationship between the initial volume, initial temperature, final volume, and final temperature for a fixed amount of gas according to Charles' law is given here. So we will use this expression to solve problems related to Charles' law. Let's solve few Charles' law related problems. In this problem, a gas sample is given and volume of that gas sample is 1 liter and temperature is 25 degrees Celsius. Now, if the gas is heated to 50 degrees Celsius, what happened to volume? And remember, according to Charles' law, volume and temperature are directly proportional to each other. It means if the temperature goes up, volume will also go up. So let's look at the options. First option is the volume is cut in half by doubling the temperature. That is incorrect because if you double the temperature, volume should also go up. In fact, it should also become double. So that is incorrect. The volume doubles when the temperature doubles. So this is the correct answer. Volume and temperature are directly proportional. So volume will also double if you double the temperature. Let's just check the other options too. The volume increases by a small amount. That is also incorrect. It increases proportionally to temperature, so it's not going to be a small amount. Volume decreases, that is absolutely incorrect, and not enough information, that's also not correct. So the correct option is the volume doubles when temperature doubles. In this problem, a sample of neon gas is given. So let's write down all the given values. A sample of neon gas is given and volume of that neon gas is 19.5 liter. So 19.5 liter sample of neon gas is cooled from 76 degrees Celsius to 38 degrees Celsius. So that means that the starting temperature or initial temperature was 76 and then the gas was cooled to 38, so therefore the final temperature should be 38 degrees Celsius. So T initial is 76 degrees Celsius and T final is 38 degrees Celsius. Volume is also given, so that's the starting volume, 19.5. So V initial is also given, so V initial is 19.5 liters. And what do we want to find? What is the volume of neon in liters at this lower temperature? So at final temperature, what will be the volume? So that's what we want to find. And remember, the Charles law states that V initial divided by T initial is equals to V final divided by T final. Before we plug in the values, we must convert temperature into Kelvin scale. So temperature should be in Kelvin scale. But our temperature is not given in Kelvin, it is given in degrees Celsius. So let's convert temperature in Kelvin scale. So we know that T Kelvin is equals to T Celsius plus 273. So therefore T initial in Kelvin scale would be 76 plus 273 and T final in Kelvin scale will be equals to 38 plus 273 in Kelvin scale. So if we add them up, so T initial will come out to be is 349 Kelvin and T final in Kelvin scale will be 311 Kelvin. So let's plug in the values. Before we plug in, let's reshuffle the equation so that V final is on one side and everything else is on the other side. So this equation will transform into, so V final is equals to, so V initial times T initial multiplied by T final. So let's now plug in the values. V initial is 19.5 liters multiplied by T final is 311 Kelvin and this is divided by T initial, which is 349 Kelvin. So Kelvin cancels with Kelvin, and if we multiply the numbers and then divide, we get 17.4 liters. So that is the answer. The relationship between temperature and pressure of a gas is given by Gay-Lussac's law. This law states that the pressure and the temperature of a fixed amount of gas are directly proportional to each other. It means that if temperature of a fixed amount of gas goes up, the pressure of that gas will also goes up by equivalent amount. So therefore a plot or a graph between pressure of a gas and temperature of a gas will be a straight line. At high temperature, pressure will also be high, and as the temperature goes down, the pressure will also go down. Consider a fixed amount of gas in a barrel as shown in this in this figure. When the gas is heated from 200 Kelvin to 400 Kelvin while maintaining the constant volume, so the volume does not change, the pressure inside the barrel increases as shown in this picture. So because the temperature went up by double amount, in order to maintain the same volume, we have to increase the pressure uh, by the same equivalent amount. So pressure also has to go up by double amount. So only then the volume will be maintained constant. So in other words, if the temperature of a gas goes up, the pressure also goes up. When doing calculations using Gay-Lussac's law, temperature must be given in kelvins. And the expression to solve problems related to Gay-Lussac's law is Pi over Ti equals Pf over Tf, where Pi and Pf are pressure values at initial and final states, whereas Ti and Tf are the temperature values at initial and final states. The combined gas law incorporates all simple gas laws, that is Boyle's law, Charles' law, and Gay-Lussac's law into one law. The combined gas law is used when there is a fixed amount of gas N and variable values of pressure, volume, and temperature. The combined gas law in terms of initial and final concentration can be expressed in this form. Pi times Vi divided by Ti equals Pf times Vf divided by Tf. Remember, the value of temperature must be in Kelvin scale. Let's apply combined gas law to solve this problem. At a pressure of 4.2 atmosphere and 11 degrees Celsius, a nitrogen bubble in the skin of a diver has a volume of 0.01 ml. What will the volume be when the diver ascends to sea level at 29 degrees Celsius? So it's a long statement. So let's find what values are given to us. At a pressure of 4.2 atmosphere, it means the value of initial pressure Pi is given as 4.2 atm and 11 degrees Celsius, so therefore the initial value of temperature is also given. So Ti is 11 degrees Celsius, and we know that temperature must be in Kelvin. So let's change this to Kelvin scale. So that will be equals to 11 plus 273 Kelvin, or Ti will be equal to 284 Kelvin. A nitrogen bubble in the skin of a diver has a volume of this much. So therefore the initial value of volume is also given, which is 0.010 ml. What will the volume be? So it means that we want to find the final volume. So V final is unknown when the diver ascends to sea level. So it means the finally diver goes back all the way up to sea level. So what is the pressure value at sea level? We know that pressure value at sea level, that's the final pressure, is equals to 1 atmosphere, because at sea level pressure becomes 1 atm, and T final is also given, which is 29 degrees Celsius. And let's convert it into Kelvin. And to convert it into Kelvin, we need to add 273, and when we do that, it comes out to be uh, 29 plus 273 Kelvin. So that's 302 kelvins. Okay, so according to the combined gas law, Vi times Pi divided by Ti is equals to Pf times Vf divided by T final. Now the unknown is Vf, so let's reshuffle the equation to have that unknown value on left hand side, everything else on the right hand side. When I reshuffle the equation, it becomes Vf is equals to Pi times Vi divided by Ti multiplied by T final divided by P final. So all we now need to do is plug in the values and find the final volume. So therefore Vf will be equals to, let's plug in the value in this equation. P initial is 4.2 atm multiplied by V initial, which is 0.010 ml, divided by T initial, which is 284 Kelvin, multiplied by T final, 302 Kelvin, divided by initial pressure, which is 1 atmosphere. Atmosphere cancels with atmosphere, and Kelvin cancels with Kelvin, so we have final value in units of milliliter. So let's uh, refine this equation. So this will be equal to 4.2 times 0.010 times 302 divided by 284, that many ml. So let me use the calculator to perform this mathematical calculation. So this value comes out to be 12.68 divided by 284 milliliter, and the final number is, let me divide, 0.045 milliliter. So that will be the final answer. So the volume of the nitrogen bubble, which will form in the skin of a diver, will expand to 0.045 at sea level. So therefore, when divers ascend from the deep ocean to the sea level, there is always a danger of bubble formation in the blood vessels, which can be fatal. So therefore divers ascend very slowly so that all the bubbles which form, they dissipate. All the gas laws that we have described so far, the amount of gas has remained constant. In this section, we will consider the relationship between moles of a gas and its volume. The relationship between the volume of a gas and its number of moles is given by Avogadro's law. According to Avogadro's law, the moles of a gas N is directly proportional to its volume V. And remember, in this relationship, the value of temperature and pressure remain constant. So in other words, if the number of moles of gas goes up, the volume will also goes up. We observe Avogadro's law anytime we fill a balloon. For example, when helium or any other gas is added to balloon, the number of gas atoms in the balloon increases, and so does the volume of a balloon. So air goes in, and more air goes in, bigger will be the balloon. More gas, so more will be the volume of the balloon. So that is essentially Avogadro's law. The mathematical expression for Avogadro's law is given here. So it is VI over NI equals VF over NF, where VI and VF are initial volume and final volume, and NI and NF are initial number of moles and final number of moles of the gas. A sample of 2 moles of a gas occupies volume 1.0 liter. What will be the new volume when another 1 mole of gas is added? So it means our starting number of moles is equals to 2, and our starting or initial volume is 1.0 liter. And we want to find the final volume, and the final number of moles is, we started with 2 and 1 is already 1 mole is also added to it, so therefore final number of moles will be 3. So let's write all the values which are given to us. So Ni is given to be 2 moles and Vi is 1.0 liter, and final is 2 mole plus 1 mole. So this is equals to 3 moles. And we want to find V final. And according to Avogadro's law, V initial divided by N initial is equals to V final divided by N final. So if let's reshuffle the equation, and so that we get the V final on left hand side. So V final will be equals to V initial divided by N initial multiplied by N final. So let's plug in the values. So V initial is 1.0 liter divided by N initial is 2 moles multiplied by N final, which is 3 moles. So moles are cancelled with moles. So answer will be 3 times 1.0 divided by 2. So this will come out to be 1.5 liters. So correct answer is 1.5 liters. A common reference condition used when measuring the properties of a gas is standard temperature and pressure, and it is denoted by STP. STP stands for standard temperature and pressure. These are the standard values of temperature and pressure at which properties of gases are measured. The standard temperature value is 0 degrees Celsius or 273.15 Kelvin. Many times we just simply take it as 273 Kelvin. And the standard value of pressure is 1 atmosphere or 1 atm. 1 mole of any gas at standard temperature and pressure will always occupy 22.4 liters of volume. So in other words, at STP, volume of 1 mole of any gas, regardless of which gas we are talking about, any gas, they all have same volume, and that volume number is 22.4 liters. So for example, if we have three balloons and each of these three balloons are filled with three different gases, and the temperature of those gases is 0 degrees Celsius and pressure is 1 atmosphere, the volume of all of these gases will be 22.4 liters. So because this is the volume of 1 mole of gases, therefore this volume is also known as molar volume. So we can say molar volume of any gas at STP is 22.4 liters. We can use molar volume formula as a conversion factor. We can write at STP. This is important. This can only be used at standard temperature and pressure. 1 mole of gas is equal to 22.4 liters. So we can use this statement as a conversion factor to solve many problems. Let's take a look at one of the problem in which we use the molar volume equation. So the problem is, what volume will 2.0 mole of oxygen occupy at STP? See, whenever you see this at STP, then we can apply the molar volume equation. We know at STP 1 mole of gas is equals to 22.4 liter. Now this is common for any gases. In our example we have oxygen, but regardless of any gas we can always use this as a equality statement to figure out the conversion factor. So we can write that equation on the side. So let's see what is given to us. So number of moles given to us are 2.0 moles, and we want to find volume. So it means we need to go from moles to volume, and we need a conversion factor, and that conversion factor will come from this equation. And remember, this equation is only valid whenever the gas is at STP, and our gas indeed is at STP, so we can use this equation. Remember, we cannot use this equation if the temperature and pressure are not standard values. Okay, so let's continue, because in this case our sample gas is indeed at STP. So how many moles are given? So we have 2.0 moles multiplied by conversion factor. So this mole will be down here, so 1 mole and top value will be 22.4 liters. Mole cancels with mole, and the answer comes out to be 44.8 liters. So therefore correct answer is this option. Density of a substance is equal to mass divided by volume. This is the formula of density. Now in chapter number 5 we learned that mass of 1 mole of any gas is equals to mass of 1 mole is equals to its molar mass. And in this chapter we learned that volume of 1 mole of a gas is equals to 22.4 liter. And yes, I know this formula only works at STP, so let's put that in. But the mass of 1 mole is independent of STP, so therefore this also works at STP, but the volume only works at STP. But in any case, if we have a gas at STP, we know that mass of 1 mole of that gas is equals to molar mass of that gas, and volume of that 1 mole of gas is equals to 22.4 liter. So by substituting these values in the density formula, we can calculate density of a gas. We can use the mass of 1 mole of gas equal to its molar mass and the volume of that 1 mole of gas equal to 22.4 liters. By plugging in these values, we can calculate the density of a gas at STP. For example, if we want to calculate the density of helium, we will take the molar mass of the helium from periodic table, which is 4.00 grams per liter, and molar volume is 22.4 liter. If we plug in those values, the density of helium comes out to be 0.179 grams per liter. Okay, so let's calculate density of some other gas. So in this case, we want to find the density of carbon dioxide. The molar mass of carbon dioxide is already given to us and at STP. So let's find the density of carbon dioxide. So we know that density of gas at STP, this is important, this is only at STP, is equals to molar mass divided by molar volume. Molar mass is given to us, this is 44.01 grams per mole, and molar volume we know is 22.4 liters per mole. Liters per mole means it is the volume of 1 mole of that substance. So moles and moles cancel, and if we divide 44.01 with 22.4 liters, the answer comes out to be, let me use my calculator, the answer comes out to be 1.965 grams per liter. So this is the density of carbon dioxide. So density of CO2 is 1.965 grams per liter. Next question is, will carbon dioxide sink or float in air? Now density of air is given, which is 1.29 grams per liter. So now carbon dioxide density is higher density than air. Therefore, carbon dioxide will sink. So any substance which has higher density will sink than the substance which is at lower density. So lower density things will stay up and higher density things will go down. So CO2, because its density is greater than the density of air, therefore CO2 will sink in air. In the definition of atmospheric pressure, we learned that the pressure exerted by the atmosphere around the planet Earth is 1 atm. Now we know that the atmosphere around planet Earth is consist of multiple gases. It is made up of nitrogen, oxygen, argon, carbon dioxide, and many other gases. Now when we have a mixture of gases and their combined pressure is known, for example in atmosphere, all these mixture of gases exert 1 atmosphere pressure, then how do we know what is the pressure of individual component of the gas? Okay, so together we know that all these gases exert 1 atm of pressure, but what is the individual pressure of each of these gases? Do they all exert 1 atm or less than 1 atm? How do we know? Dalton's law talk about the individual pressure of components of a mixture of gases. Dalton's law show that for a mixture of gases, each gas exert a pressure independent of other gases behaving as if it alone occupied the total volume. The pressure of a gas in a mixture of gases is known as partial pressure. So if we have n number of gases in a mixture, then the total pressure will be equal to P1 plus P2 plus P3 and so on, where P1, P2, P3 are individual pressures of all the components of gases. So this law is known as Dalton's law of partial pressure. Dalton's law can also be used to calculate the partial pressure of any gas as long as the percentage of that gas in the mixture is known. For example, we know that the percentage of oxygen in air is about 21%. So if we want to calculate the partial pressure of oxygen at sea level, we know the total pressure is 1 atm. So P total is 1 atm at sea level. So if you want to calculate the partial pressure of oxygen, so PO2 will be equals to, so partial pressure of any gas is equals to fraction of that gas multiplied by the P total. By using this formula, we can calculate the partial pressure of any gas. So for example, in case of oxygen is 21%, so fraction is equals to percent divided by 100. So therefore, it is equals to 21 divided by 100. That's how we calculate the fraction multiplied by P total. P total is 1 atm. So therefore, partial pressure of oxygen is 0.21 atm. Similarly, you can calculate partial pressure of any other gas as long as you know the total pressure and the percentage of that gas in the mixture. And if you add all the partial pressures, you will get the total pressure. Let's solve this problem based on Dalton's law of partial pressure. A mixture of only nitrogen and oxygen has total pressure of 3.00 atm. So P total is given to us, that's 3.00 atm. And we have a mixture of oxygen plus nitrogen, only two gases. Also, the partial pressure of oxygen is also given. So partial pressure of oxygen is 0.63 atm. And what is the partial pressure of nitrogen in the tank? So that's what we want to calculate. We know that P total is equals to the sum of partial pressures of individual components. So that will be P oxygen plus P nitrogen, where P oxygen is partial pressure of oxygen and P nitrogen is partial pressure of nitrogen. So let's plug in the values. So P total is 3.00 atm and P oxygen is 0.63 atm plus P nitrogen. If we reshuffle this equation, so P nitrogen will be equal to 3.00 atm minus 0.63 atm, and this comes out to be 2.37 atm. So that's how we can calculate the partial pressure of other gas as long as we know the total pressure and the partial pressure of oxygen. Heliox is a mixture of helium and oxygen that in some cases contains 60% helium. If the total pressure is 700 mm mercury, what is the partial pressure of oxygen? Okay, so let's think about it before we figure out the answer. So we have a gas mixture, it's a mixture of helium and oxygen, and the mixture contains 60% helium. So that automatically means the percentage of oxygen will be 40% because we have only two gases and together they are 100%. So we now can figure out the percentage of oxygen, which is 40%. So P total is also given. So P total or total pressure is 700 millimeters of mercury. And what do we want to find? We want to find the partial pressure of uh, oxygen. So this is unknown. We know that P total is equals to partial pressure of oxygen plus partial pressure of helium. But the problem is we don't even know the partial pressure of helium. This we know. We don't know this. We don't know that. If we can figure out the partial pressure of helium, then we can plug in the value of helium, plug in the value of total pressure, and we can figure out the value of partial pressure of oxygen. So let's see if we can calculate the partial pressure of helium. In a couple of slides earlier, we learned that partial pressure of any gas can be determined as long as we know the total pressure as well as its percentage. We already figured out that the percentage of oxygen is 40%. So therefore, partial pressure of oxygen is equals to fraction of oxygen multiplied by P total. So, and fraction is percentage divided by 100. So 40 divided by 100 multiplied by total pressure, which is 700 millimeter mercury. And when we solve this, and this comes out to be 280 millimeter of mercury. So partial pressure of oxygen comes out to be 280 mm mercury, and that is the correct answer. With that, we conclude chapter number 7. In this chapter, we discussed what are the changes in state and what happens to energy, whether it's exothermic or endothermic, if a state changes from solid to liquid or liquid to gas. And then we learn about various laws on which the properties of gases depends. And then finally, we talked about the partial pressures of oxygen and how the total pressure depends on partial pressure of individual components of a mixture of gases. If you have any question, please let me know. Thank you for watching. Have a wonderful rest of the day. Bye bye.